Hey guys, Mr. Hedrick here with one more video on Unit 3 that will wrap up this unit and then leave us with one more to cover this semester. And this last video will be on the remaining key features of graphs of polynomial functions that we can use to find different interesting things. So we're going to start today by looking at when a graph increases and decreases and how you can tell. So you're always going to start from the left side of the page, wherever that graph is, and trace your finger towards where it's heading. So in this case, you can see that the graph will head up, then turns back around and heads down, and then back up and back down. So in other words, it increases, then decreases, then increases, and finally decreases towards the end. It heads downwards forever, off to the right. So read the graph from left to right. When does it go up? When does it go down? Write out that pattern. Increase, then decrease, then increase, then decrease. The number of turning points on a graph is next, and we can find that by seeing the number of times it turned around, changed direction. And in this case, that happened 3 times. Notice this will always match the number of dashes that you have in your increase-decrease pattern, right? You increase, then you decrease, then you increased, then you decrease one more time, 3 turning points there. That matches your graph and it having 3 turning points as well. Finally, local min and local max are the highest or lowest turning points. Sometimes on graphs we have more than one turning point, and we want to always look at what's the highest for the local max and what's the lowest for the local min. So we're just taking a snapshot of this graph. Obviously the graph goes off the page, those arrows indicate that, but whatever we're given on this graph will have sometimes a local max, local min, just depends. What's the highest turning point here? Actually, these 2 points are equally high, right? Now in other cases, like we're going to see later, in a final example that wraps everything together, there might be one rather than another. In this case, there's actually 2 local maximums because both of those turning points are the highest turning points, and you can see that by the y-coordinate here. So we have one local max at 2, 2, right? That would be this one. We have another local max at 0, 2, right? Same y coordinate here as the other one. Those turning points are what we would use to look at what's highest, but in this case both were the same. This one down here is actually our local minimum, right? That's at 1, 0. This is our local minimum because it's the lowest turning point. It's the turning point that is lowest out of all of our turning points on this graph. So that's how you would identify those 3 key features. So we're going to return to those in a little bit. But for now, we're going to move on to other key features. So for example, from a graph, you can not only tell what we just did, you can also find things like whether the lead coefficient is positive or negative, whether the degree is even or odd, and from that determine end behaviors. So the lead coefficient is always going to be positive if the graph increases last. So in this case, the graph decreased then increased. That's a positive lead coefficient. Same thing down here actually. Notice this graph's increasing the whole way, it's never decreasing. It kind of looks like it would start to, but it flattens out, still heads up at the end. Increases at the end means that it's a lead coefficient that's positive. If the graph decreases last, so in this case the graph increased then decreased, the lead coefficient is going to be negative. Same thing here, the graph decreases the whole time. Last thing you see there, lead coefficient must be negative because it's decreasing. We can also determine the degree, whether that's even or odd. Remember, your degree is the largest exponent of whatever function that matches these graphs. All of these graphs match some function, right? F of x equals something. And for whatever that function is, it'll have a largest variable exponent, typically. So in this case, what would that largest variable exponent be? Would it be even or odd? In this case, it would be even. And the reason that you can determine that is notice that these arrows here both point the same direction, up. Okay. Same thing here, the degree is even because both arrows point down. Okay. Here, notice that the arrows are opposite, opposite O, odd O. Okay, if the arrows point opposite directions, the degree is odd. And this is going to help you to determine end behavior. These are the 4 scenarios, the only scenarios that can occur. When your lead coefficient is positive and the degree is even, when your lead coefficient is positive and the degree is odd, when the lead coefficient is negative and the degree is even, when the lead coefficient is negative and the degree is odd. Those 4 scenarios are the only ones that can occur, at least for our purposes in this unit. So you can see that the end behavior here in words, 2 arrows, these are your end behaviors. Okay. As we walk towards the right side of the graph or look towards the right along the x-axis, where does the graph head towards? Positive infinity. As we walk along the x-axis towards negative numbers, towards negative infinity, where does the graph head? Again, upwards towards positive infinity. In both cases, the end behavior is towards positive infinity for the graph. Versus, check out these end behaviors here. Where do they head? Again, as you head along the x-axis towards negative infinity, the graph heads downwards towards negative infinity. As you were looking towards, or if you would look along the x-axis towards the other side, towards the left, towards negative numbers, not positive, that should be positive infinity. If you look towards negative numbers, where does the graph go? Again, towards negative numbers, towards negative infinity. So you're always looking left and right. Towards negative infinity, towards the left, towards positive infinity, towards the right, and checking out where your arrows are. In this case, they were towards positive infinity, both of them. In this case, they were towards negative infinity, left and right, both of them. Now, for the ones down here, obviously they're opposite. So as we head towards positive infinity towards the right, the graph heads up towards positive infinity, whereas as we head towards the left, right, as our graph, if we look towards the left side of the page, the graph clearly is going not up, but down towards negative numbers, towards negative infinity. Same thing with this last graph. As we head towards positive infinity towards the right, where's the graph heading? Down, towards negative numbers, towards negative infinity. As we head towards the left side of the page, towards negative numbers along the x-axis, towards negative infinity, where does the graph go? Upwards forever towards positive infinity. It goes left and right forever, up and down forever, but opposite end behaviors in this case. So that would be how you find end behavior. That will always match those 4 scenarios. It just depends on what type of graph that you have. One more thing that we'll talk about to wrap up this unit and then do one last problem that puts everything together is intervals of increase, decrease, and intervals of positivity and negativity. So this is just determining where on the graph specifically does it increase, where does it specifically decrease. So notice here, our graph increases, then decreases, then increases. So we actually have 2 arrows pointing up, 2 intervals of increase, right? Increase, decrease, increase. 2 intervals of increase, 1 interval of decrease. Now, the decrease one might be easier to see. Notice that the graph is decreasing from here to here. And we're always going to look at the x-axis, those numbers, those x-coordinate points. So the graph is decreasing from 0 to 2. 0 until 2 along the x-axis. This would be our interval of decrease. Okay. Decreasing along that interval. Whereas it increases in 2 different places. So, does it ever stop increasing at the beginning? No, it's increasing forever coming from negative infinity. It is always increasing from the very beginning towards the left. Okay? And it increases until 0. Then you hit a turning point, right? 0, 2. Okay? You hit that turning point, you turn around. That x-coordinate there is 0. It stops increasing. It starts to decrease from 0 until 2. Then it stops decreasing because, again, you turn around, and starting at 2 and going off to the right forever, off towards the right side of the page, does the graph ever stop increasing? No. It increases forever after positive 2. That's the interval of increase and decrease. Write out your IDI pattern or whatever your pattern might specifically be. And notice here, 2 intervals of increase, 1 interval of decrease. Okay. Check out your arrows, see where those arrows start and stop. Interval of positivity and negativity just asks you for where's the graph above or below the x-axis. So here, in this case, the graph is below the x-axis. There, everywhere from the left until it crosses the x-axis at -1, 0. So in this case, interval of negativity will be from -infinity until -1. All the way off towards the left side of your page until that x-coordinate point at -1. Then it's positive, right? It jumps above the x-axis from everywhere after -1 until touches the x-axis at 2. Okay? Then it's not above the x-axis anymore, right? It's on top of it. And then what does it do? Does it go up or down, above the x-axis or below? It goes above the x-axis again after 2, all the way off to the right forever. It never comes back down. It increases forever, but that's not the important part. The important part is it's above the x-axis, just as this was above the x-axis. So you're circling basically, make marking points. Where are your x-intercepts? You got 2 of them. Where are the graphs above or below the x-axis? In this case, you had one area that was below, or one interval below, right? One interval of negativity, and then 2 intervals of positivity separated by that x-intercept. So that is the last new material for the unit. And now we're going to look at a graph that puts all of this together that we've talked about in our last 2 videos. So a lot of information here. None of it particularly difficult if you've practiced with it enough, and that's what I'm going to recommend that you do after this. Okay, so taking a look at this graph, I would try this on your own first to identify all of these different key features, and then follow me as I'm doing these on my own. The y-intercept here, for example, x comma y, 0 comma -2. That's where the graph crosses the y-axis. Versus the x-intercepts, where does the graph cross the x-axis? In this case at 1, 2, 3, -4, 0, and -1, 0, and lastly 3, 0. Okay, x, y. Look left and right first, and then up and down. So the x-intercepts will help us to find the real roots. Remember, these are roots that don't involve I. I would have to tell you if you had those or not. Anything that involved imaginary numbers. Let's assume that there are no complex roots for this graph, so keep it nice and simple. The real roots have to be -4, -1, and 3. Those are the 3 x coordinates that would turn everything into 0 if you plugged it into the function that this graph matches, as we'll see in a second here. So -4, -1, and 3. Multiplicity, remember that comes from the behavior of the graph. We talked about this in our last video. The shape of the graph here at this x-intercept is a U, and U means multiplicity of 2. Versus this is like a straight line, another straight line, multiplicities of 1. The only other type of multiplicity that you could have would be something that looks like this, and that's a multiplicity of 3. We don't have that on this graph. We just wanted to remind you of that. If it is an S-shaped curve or flattens out along the x-axis but still goes in the same general direction, multiplicity there is a 3. Okay, so we don't have that here. Instead, we have our degree coming from our multiplicities, adding all of those up. 2 plus 1 plus 1 is degree 4. So it's not degree 3. Yes, we do have 3 x-intercepts, but multiplicities were different for a couple of those. This one had a multiplicity of 2, plus 1, you add the multiplicities. Notice 4 is an even number, right? The degree is even, which makes sense because these end behaviors point in the same direction. So it can't be odd. It has to be even. So if you ever get tripped up, it looks like there's only 3 roots. Well, actually there's 4. The degree has to be even. So be careful about that. Add up your multiplicities, not just the numbers on the left here. And therefore, the possible factorization of this problem, or where did this problem come from, right? What matches this graph, roughly speaking? Where did -4 come from? A parentheses with the opposite sign and an exponent here of 2. -4 is a solution twice. Okay, for 2 parentheses, x plus 4 times x plus 4. -1 is another root 0 or solution. Where did that come from? Must have come from x plus 1, a parentheses with the opposite sign, because -1 plus 1 is 0. And lastly, same thing here. That'd be x minus 3, parentheses with the opposite sign, because 3 minus 3 would be 0. So this is, if you graphed this, it would give you some sort of function that looks very similar to what we have on the board. It might not be to scale as far as the length, but it would have the same shape as these specific behaviors around the x-intercepts. So let's take a look now. Given what we have from our last video, what else have we learned today? Our increase-decrease pattern is, in this case, decrease, increase, decrease, increase. So di, di, as I would write it. Number of turning points then must be 1, 2, 3. 3 turning points, which makes sense because that's the number of dashes that we have here. Local minimum. Okay, so you notice that we have 2 turning points that change direction back to increasing. 2 turning points that look like a U shape. But this one is lowest, so this is really your local minimum. This is a relative minimum, but it's not the actual local minimum. Right? Relatively speaking, this turns things around as a U shape, but this would be our local minimum, and that's coordinate point 1, comma, -3, approximately, right there. Local maximum, we only have 1 turning point that's shaped like a rainbow, so clearly the local maximum has to be this turning point at -3, comma, +2, roughly speaking, again. We said the degree has to be even because the arrows point the same direction. We also know that the the lead coefficient has to be positive because our graph increases at the end. Okay, so that helps us with end behavior now. Notice, as x heads towards positive infinity, as we go towards the right side of the page, where does the graph go? It goes up towards positive infinity. And since the degree is even, the other end behavior should be the same, and it is. As we go towards the left, if we look towards the left side of the page, as x approaches negative infinity along the x-axis towards the left, what does the graph do? It goes up again towards positive infinity. Same end behavior because the degree is even. And the lead coefficient is positive, so they're heading towards positive infinity. Interval of increase, interval of decrease. Notice we have 2 decreases, 2 increases, so we'll have 2 of each. Okay. Intervals of decrease. So we're decreasing from negative infinity all the way down until -4, right, along the x-axis. Then we turn around, so negative infinity until -4. Then we start to increase from -4 until -3 along the x-axis. We're increasing, stop, turn around, decrease from -3 all the way until x equals 1. And another way to write the and symbol, by the way, is that little u. Okay. This just means and, it means the same thing, if you ever see that as far as notation goes. And lastly, everything after 1 increases off to the right forever towards positive infinity. The graph is increasing at the end from this starting point, x equals 1, all the way off to the right. And lastly, interval of positivity, negativity, where's the graph above or below the x-axis? It's below the x-axis here from -1 until +3. It is positive or above the x-axis in 1, 2, 3 locations. Okay? It's positive from the left side of the page all the way until that x-intercept of -4. And after -4, because the graph does touch that x-intercept, it's not above the x-axis here. But after it, it's above the x-axis from -4 until -1, right? Along the x-axis, it's above the x-axis here until -1. When it becomes negative, until +3. And then everything after that, again, off to the right forever. 3 until infinity. Okay. The graph is positive, it's above the x-axis. And that wraps up our unit. So again, from a graph, this very simple graph, you can tell a lot of information. So this does require you to practice the problems. Go to the e-class page, activities, assignments. You got some practice there that you can work on. Get your test review. We will be going over that next. But this does wrap up Unit 3, so we do have one more unit to get to. That'll come after our break. And then we'll have our final exam. So coming down to the end of the semester, get the practice in that you need. Come to me with any questions. And I'm looking forward to ending this strong with you guys.